For more than half a century, one question has haunted astronomers more than any other. Not whether planets exist somewhere across the vast expanse of the galaxy, but whether they exist right next door. Alpha Centauri, the closest star system to our sun, has always carried a weight that no other target in the sky can match. Close enough to imagine reaching, similar enough to feel familiar, and yet, year after year, decade after decade, stubbornly, almost defiantly, silent. The hope was reasonable. Alpha Centauri A is not some exotic alien star burning with unfamiliar chemistry. It is nearly a perfect mirror of our own sun in mass, temperature, luminosity, and age. If planets were going to form anywhere in the universe outside our own solar system, the logic said they would form here. They would form around a star that behaves exactly like the one we already know can support worlds. And they would form close enough that one day, with the right technology, we might actually be able to reach them. That hope was not naive. It was scientifically grounded, mathematically supported, and emotionally powerful. It made Alpha Centauri the most searched, most discussed, most anticipated planetary system in the history of astronomy. And it kept failing. Radial velocity surveys, which detect the gravitational tug of orbiting planets on their host stars, returned nothing reliable. Transit searches, which look for the faint dimming caused when a planet crosses in front of a star, found no consistent signals. Each new instrument, each new technique, each new generation of telescopes was pointed toward Alpha Centauri and came back empty. The null results accumulated quietly, without drama, without announcement, just absence stacking on absence. Slowly, the confidence began to erode. Researchers who once treated Alpha Centauri as an almost certain source of planetary discovery began to wonder if something fundamental was different about this system, if the closeness that made it so appealing was masking a deeper problem. The difficulty was not just the emptiness, it was the star itself. Alpha Centauri A is bright enough to see with the naked eye, and that visibility, that quality which has made it a landmark in the southern sky for all of human history, becomes a catastrophic liability for precision instruments. It overwhelms detectors, it saturates sensors, it floods the surrounding field with scattered light that buries any faint signal trying to emerge beside it. And Alpha Centauri A does not sit alone. Its companion, Alpha Centauri B, orbits it in a tight binary dance, constantly shifting position, constantly contaminating observations with its own overlapping glare. The pair moves across the sky rapidly enough that long-term monitoring requires constant recalibration. Every time astronomers tried to look carefully, the system seemed to actively resist being studied. The closer they looked, the harder it pushed back. By the time James Webb launched in 2021, Alpha Centauri had transformed psychologically in the minds of many researchers. It was no longer the promising neighbor waiting to reveal its secrets. It had become an unresolved problem, a system that should have cooperated and refused to, a star that should have given up its planets by now and had not. Some researchers began asking the darker question: what if Alpha Centauri A never formed planets at all? What if the gravitational chaos of the binary system stripped the protoplanetary disk too early, preventing orderly growth from ever taking hold? What if absence was not a detection limit but a true result? Then James Webb did something it was never designed to do, and what it found did not bring the relief that decades of searching had been waiting for. It brought something far more unsettling. In August 2024, James Webb turned its instruments toward one of the brightest stellar systems visible in the sky, and in doing so, broke nearly every rule that governs safe exoplanet observation. The target was Alpha Centauri A. The instrument was MIRI, the mid-infrared instrument, designed to detect the faint thermal glow of cold, distant objects in deep space, not to stare directly into the blazing heart of a nearby stellar system. The operations team at NASA had to design a custom observing sequence from scratch, a tailored set of procedures that existed for no other target in the telescope's entire program. The extra effort, as one researcher put it, paid off spectacularly, but not in the way anyone had prepared for. After hours of observation and months of painstaking data processing, something emerged from the overwhelming glare. A faint, coherent point of light appeared at a projected distance of roughly 2 astronomical units from Alpha Centauri A, corresponding to an angular separation of 1.5 arcseconds. It was not marginal. It was not buried at the edge of detectability where wishful thinking could construct a signal from nothing. The detection reached a statistical significance of 5.5 sigma. In the language of physics, sigma measures how far a result sits from what pure random noise would be expected to produce. 5 sigma is the standard threshold for a confirmed discovery in particle physics. 5.5 means that the probability of this signal being a random fluctuation is so vanishingly small that it is, for practical scientific purposes, ruled out. The team did not celebrate. They interrogated the detection with the same intensity they would apply to any result that seemed too good, too convenient, or too surprising. Every known source of contamination was tested and retested. Background stars were eliminated using the Gaia catalog, the most precise stellar position database ever assembled. Distant background galaxies, which can mimic point sources at certain wavelengths, were ruled out by analyzing the spectral behavior of the signal. Moving objects within our own solar system, which drift across the field during long observations, were excluded by tracking positional motion throughout the exposure itself. Instrumental artifacts, the false signals that can be generated by the telescope's own optics when pushed near its limits, were tested through injection and recovery experiments specifically designed to expose false positives. S1 survived all of it. The team then split the raw data into independent subsets and processed each one separately. The same signal appeared consistently across every partition. Whatever S1 was, it was not a processing error, not a catalog gap, not a statistical ghost. It behaved exactly as a real astrophysical object gravitationally bound to Alpha Centauri A would be expected to behave. For the first time in more than 50 years of searching, a planet candidate beside our nearest solar twin moved from the realm of speculation and theoretical possibility into the domain of measurable, statistically robust, peer-reviewed evidence. Confirmation, researchers assumed, would be straightforward. Planets move. Their orbital motion is predictable. Follow-up observations were scheduled. The same instruments, the same pipeline, the same reference stars. All that was needed was for S1 to appear again in its expected position, shifted slightly along its orbit, and the discovery would be locked in. Instead, what came back from those observations would force astronomers to confront something far more difficult than a simple non-detection. Follow-up observations were conducted in February 2025 and again in April 2025, both using directors' discretionary time, which is reserved for the most urgent and scientifically significant targets. The telescope performed without fault. The same processing pipeline that revealed S1 in August was applied identically. The same reference stars were used for calibration. The same coronagraphic techniques suppressed the glare of Alpha Centauri A, and the region where S1 had appeared so clearly with such statistical confidence showed nothing. No trace, no marginal residual, no hint of a signal, just the flat, featureless noise of empty space where a planet had stood months before. The team's reaction was not disappointment. It was something closer to genuine unease, because the disappearance violated a foundational principle of orbital mechanics. Gravity does not allow objects to simply cease to exist. A planet cannot decide to stop being a planet between observations. Whatever had been there in August was either never real in the first place, or it had moved somewhere the telescope could not follow. Both possibilities carried their own weight. Neither offered comfort. 3 explanations survived the analysis. The first was a catastrophically rare statistical fluke, an event so unlikely that a 5.5 sigma signal fooled every verification test simultaneously. This explanation is scientifically acceptable, but deeply unsatisfying, because it would mean that one of the most rigorous detection processes in the history of exoplanet science produced a false alarm. The second was an unknown background source, an object not present in any catalog that somehow mimicked a bound planetary companion perfectly across every diagnostic test applied. This is possible, but requires a coincidence straining credibility given the depth of the verification performed. The third explanation was the one that kept researchers engaged rather than defeated. Orbital simulations showed that if S1 is a real planet following an eccentric or highly inclined orbit, more than half of all stable orbital configurations consistent with the August detection would naturally produce non-detections in both February and April. The geometry of JWST's coronagraph is not uniform. It has regions of reduced or absent sensitivity close to the star, and those blind zones shift depending on observing angle and wavelength. In both follow-up windows, S1's predicted position placed it precisely within those regions of diminished sensitivity. The telescope was not failing to detect a stationary object. It was unable to see an object that had moved into a part of the orbit where the coronagraph goes dark. The planet had not vanished, it had moved into darkness. Crucially, a prior detection from 2019 using the Very Large Telescope, a faint candidate designated C1, was reanalyzed alongside S1. When orbital fits were run combining both detections with both non-detections, the simulations found that 52% of all stable orbits consistent with this combined picture were also consistent with missing the planet in early 2025. The disappearance was not anomalous, it was predictable. It fit the physics almost too well. What looked like a failure of detection was, in the most unsettling interpretation, evidence of an orbital architecture specifically designed by gravitational mechanics to hide itself from view. From the moment S1 appeared in the August data, the orbital dynamicists on the team registered immediate alarm. The projected position placed the candidate at roughly 2 astronomical units from Alpha Centauri A, a distance that sits uncomfortably close to the sphere of gravitational influence cast by Alpha Centauri B. In a tight binary system, the companion star does not leave orbital mechanics undisturbed. It continuously injects energy into nearby orbits, pulls trajectories off their natural paths, and over sufficiently long timescales, ejects objects outright. Stability maps computed through N-body simulations show that planets in Alpha Centauri A's vicinity are generally expected to remain stable only if their orbits stay below 3 astronomical units in semi-major axis. And even within that range, inclination matters enormously. Orbits tilted near 90 degrees can become unstable at distances as close as 0.23 astronomical units. S1 appeared exactly where long-term survival should be unlikely unless very specific orbital conditions are met. This was not a small discrepancy between observation and model. It was a direct confrontation between what the telescope found and the mathematical frameworks astronomers rely on to define what is even physically possible in a system like this. The simulations that followed showed that S1 can survive, but only under restrictive conditions. Either its orbit is highly eccentric, stretching far from the star before looping back inward and spending most of its time in safer gravitational territory, or its orbital plane is significantly tilted relative to the plane of the binary system, reducing the cumulative gravitational interference from the companion. Both of these survival scenarios share a common consequence. They produce orbits that are naturally difficult to detect with coronagraphic imaging. The eccentricity carries the planet into coronagraphic blind zones during parts of its orbit. The inclination changes the apparent position on the sky in ways that complicate follow-up scheduling. Stability in this case does not look like calm, predictable circular motion. It looks like evasion. If surviving there is difficult, forming there is harder still. In the early stages of Alpha Centauri's history, the gravitational influence of the companion star would have stirred the protoplanetary disk around Alpha Centauri A violently. Increased collision velocities between dust grains would have caused destruction rather than accumulation, preventing the slow, orderly coalescence that planet formation requires. Cambridge research into binary system planet formation found that planetesimals need to start at least 10 kilometers across, and the disk itself must remain close to circular without major irregularities for growth to proceed in a system like this. These conditions are achievable but not guaranteed, and their presence in the early Alpha Centauri system remains entirely unknown. If S1 exists where observations suggest, it either formed much closer to the star and migrated outward into its current configuration, or it formed under local conditions that current theoretical models do not adequately describe. Both options require revising frameworks that have successfully explained thousands of planetary systems across the galaxy. S1 is not asking for a minor correction. It is asking for an explanation that does not yet fully exist. James Webb itself becomes part of the problem. The telescope was optimized for faint and distant objects, not for targets as blindingly bright as Alpha Centauri A. The custom observing sequence, the bespoke data reduction pipeline, the carefully subtracted models of stellar glare, all of it represented the telescope being pushed past the operational boundaries its designers envisioned. Miri's coronagraphic mask blocks the star's direct light, but residual starlight still scatters through the optics in complex patterns that must be modeled and removed piece by piece. Tiny mismatches in reference star brightness or spectral type can introduce misleading residuals that look real or erase signals that are. Every step carries a dual risk, manufacturing a false positive or destroying a genuine detection. This is the most uncomfortable technical truth the Alpha Centauri observations produced. Confirmation is no longer simply a matter of more data. It is a question of whether our best instrument is capable of seeing what is physically present, given the specific geometry of each observing window. The boundary between what James Webb can detect and what remains permanently hidden is not defined by distance or faintness. It is defined by brightness, orbital geometry, and the precise angle at which a planet happens to be positioned on any given observing night. That boundary sits 4 light-years from Earth, closer than almost anything else in the galaxy, and it is not as transparent as we assumed. If S1 is real, the most immediate question is what kind of world it is. The answer from the data is almost certainly a gas giant, a planet in the broad class of Jupiter and Saturn, massive, composed primarily of hydrogen and helium, without a defined solid surface. For decades, the instinctive response to that classification would have been a quiet deflation. A gas giant is not a place where life as we understand it could exist. It has no surface to stand on, no stable liquid water, no thin, breathable atmosphere. But planetary science has quietly reframed how gas giants are understood, not as dead ends, but as gravitational anchors around which entirely different categories of world can form and survive. In our own solar system, the moons of Jupiter and Saturn host the most compelling environments for potential habitability beyond Earth. Europa holds a liquid water ocean beneath its ice. Enceladus vents organic rich plumes from a subsurface sea. Titan carries a thick nitrogen atmosphere and lakes of liquid methane. None of these are planets. All of them orbit one. A gas giant at Alpha Centauri A, near or within the habitable zone of a sun-like star, does not close the door on habitability. It opens a different one entirely. Moons of sufficient mass can retain atmospheres. Tidal heating generated by gravitational interactions with a large host planet can sustain liquid water internally, regardless of surface temperature. Long-term geological activity can cycle nutrients and maintain the chemical complexity that life requires over billions of years. The existence of S1 transforms the question from whether Alpha Centauri A can host life to whether a system of satellites orbiting a gas giant in the habitable zone of a sun-like star might already host it. One detection multiplies into an architecture of unseen possibility. The proximity of Alpha Centauri makes this possibility uniquely uncomfortable. Every other candidate for habitability discovered by modern astronomy exists at distances measured in hundreds or thousands of light-years. Alpha Centauri sits at 4.37 light-years. That is not merely closer in the sense of a smaller number on a chart. It is closer in the sense that serious scientific proposals for interstellar travel, laser-driven light sail probes, relativistic flyby missions, targeted messaging are designed specifically around this system because no other destination is physically plausible within any realistic human timescale. Breakthrough Starshot, the project backed by Stephen Hawking and Yuri Milner, proposed sending centimeter-scale probes to Alpha Centauri at 20% the speed of light. That mission was always theoretical. If S1 exists and hosts moons, it stops being theoretical and becomes directional. It stops being a demonstration of what might be possible and becomes a description of where we would actually point. The psychological weight of that shift is difficult to overstate. For 50 years, the search for planets around Alpha Centauri was motivated by proximity. Now, proximity has become something more specific, more loaded, and more difficult to sit with comfortably. If habitable environments exist 4 light-years away, then the universe is not distant and abstract. It is immediate. It is a neighbor. It is close enough that the question of what lives there, if anything does, begins to feel less like cosmological philosophy and more like something with an address. James Webb did not confirm life. It did not confirm habitability. What it confirmed is proximity wrapped in doubt. A planet that appears and disappears. A star system that resists every instrument pointed at it. A detection strong enough to matter, fragile enough to deny certainty. Alpha Centauri was supposed to reassure us. The nearest solar twin, quiet, familiar, and empty. Instead, Webb revealed a neighbor that hides its secrets well. The fear was never that something dangerous is out there. The fear is that something important might be, close enough to reach, close enough to matter, and that is exactly what we all feared.